Come on my dears, we proceed further in chapter number 4. Now we go for question number 19. Look, torque exerted on a current carrying pivoted rectangular coil. First of all, try to understand what do you mean by coil being pivoted. What do you mean by pivoting a coil? I am showing you. Suppose you have some rectangular coil. Okay. Now what do? We just fix up that rectangular coil between two pointed ends this way. Correct? Such that though it is arranged between these two pointed supports, it can rotate quite freely about vertical axis. Correct? But yet it is not getting displaced. So no translational motion, but only rotational motion. Correct? When you fix up any object between two pointed supports such that it can rotate freely about the axis passing through those two pointed supports, but it cannot get displaced, then that object is said to be pivoted. I repeat, whenever you fix up any object between two pointed supports such that it can rotate quite freely about an axis passing through those two pointed supports, but cannot perform any translational motion, then that body is said to be pivoted. Got it? Fine. Now here we consider uniform magnetic field which is applied externally between these two planar magnetic poles. This is planar magnetic north pole, this is planar magnetic south pole. You know, magnetic field is always from north pole to south pole, north pole to south pole, from north to south. It is in this direction. Correct? Fine. Now that magnetic field in the figure I have shown by this blue colored parallel magnetic field lines, which are equidistant also, which indicates uniform magnetic field. Let it be vector capital B. Don't you know vector equals to magnitude multiplied by unit vector. Magnitude is B. Unit vector in this direction means in the direction of positive x-axis is I hat. Correct? Now we consider a rectangular coil, say PQRS. Correct? In the figure we have shown only one rectangular ton, only one ton of that rectangular coil. It is PQRS. Correct? For that rectangular coil, this PQ or this side RS, they indicate breadth of a coil. PQ or RS indicate breadth of the coil. Let it be shown by symbol small b. And these sides QR and SP indicate length of the coil. QR and SP indicate length of the coil, shown by symbol small l. Then what is the area of 1 ton of a coil? It is length into breadth, length into breadth. Correct? Fine. Here we consider this rectangular coil to be pivoted in such a manner such that it can rotate freely about this vertical y-axis. Okay? Fine. If this one is positive x-axis, this one is positive y-axis, then this is origin, and positive z-axis you may consider this way, perpendicularly outside the plane of the figure. Correct? If it is perpendicularly inside the plane of the figure, we will call it negative z-axis. Okay? Fine. Now we just pass some current through this rectangular coil. Let it be capital I, which flows in this direction, P to Q, Q to R, R to S, S to P. And now, because each side of this coil is a current carrying straight wire kept in some external magnetic field, it will be exerted upon by a magnetic force given by Ampere's law, vector F equals to I into vector L cross vector B. Correct? Last time we had studied about Ampere's law. correct? What was that formula? Vector F equals to I into vector L cross vector B, and depending upon that, let us find out now magnetic forces exerted on each of these four sides one by one. Okay. First of all, I take magnetic force exerted on side PQ, and that magnetic force is suppose vector F1. As such, the formula is I into vector L cross vector B, I into vector L. But what is vector L at the time? Length vector. But right now this is not length, this is the breadth. So I should write breadth vector. So instead of vector L, I am putting vector small b cross external magnetic field is vector B, correct? The magnetic force exerted on side RS, I am taking as vector F1 dash, vector F1 dash, okay? Instead of vector F1, I just put new symbol vector F1 dash. Current is same, but the length vector you must write now minus of vector B. Why? Because direction of this current is just opposite to this, correct? So here you are taking vector small b, then here you must write minus of vector small b, minus of vector small b, correct? Cross vector B. Got it? Fine. Now these two are the forces which have same magnitude. Whatever is this magnitude, same is this magnitude. But what about their directions? I am showing you. Let us find out directions of these two forces exerted on this and this side according to right hand palm rule which I had shown last time. Remember what was that? You are supposed to expand the right hand palm in such a manner that fingers should point in the direction of magnetic field and thumb should point in the direction of current. In that case, whatever is the perpendicular coming out of that right hand palm gives us direction of magnetic force. Okay. So accordingly, let us find out now directions of these two forces one by one. First of all, we talk about vector F1. Look, I should keep my right hand this way. Then these fingers, you can see it is pointing in the direction of magnetic field. Thumb is pointing in the direction of current. Correct? This way. In this direction. Current is flowing in this direction. Okay? In the same direction I am showing my thumb. Okay? And now, if you think of a perpendicular coming out of this right hand palm, it will be coming out this way. Vertically upwards. That's why direction of vector F1 I have shown vertically upwards. Correct? But the direction you should show such that the tail of this vector must be starting from midpoint of this side. Tail of this vector must be on the midpoint of this side. Got it? What about direction of vector F1 dash? Come on, current is in this direction. Magnetic field is still in the same direction. Now you can hold the, you can expand the right hand palm such that fingers are pointing in the direction of magnetic field, thumb is pointing in the direction of current. And now a perpendicular coming out of this right hand palm will be coming out this way, vertically downwards. Correct? That's why direction of vector F1 dash I have shown vertically downwards, vector F1 dash. Correct? And that vector also you must start from midpoint of this side. Got it? Now tell me, what do you notice in the figure? These two vectors have the directions not only opposite, but lines of action of those two forces are passing through same vertical y-axis. Means they are collinear. They are collinear. Vector F1 and vector F1 dash, they are collinear. Now tell me, these two forces are collinear, meaning thereby they are exerted in such a manner such that their lines of action are coinciding, and right now that is y-axis. Okay? If you have got two forces which are equal in magnitude, opposite in direction, but if they are collinear, they cannot produce any torque. They cannot produce any torque. Okay? Because these two forces are collinear, they cannot produce any torque. So they will not exert any torque. But we are looking for expression of a torque. So now don't think of these two forces because they do not produce any torque. Then think of remaining two magnetic forces which are exerted on sides QR and SP. Let them be respectively vector F2 and vector F2 dash. Let us find out them also. First of all, vector F2, according to Ampere's law, it is current into length vector cross magnetic field vector. Current into length vector cross magnetic field vector, correct? Now, I as it is, L, vector L, vector equals to magnitude multiplied by unit vector. Now, this much is length, QR is length, QR is length. So, I must write magnitude of this vector, which is L, multiplied by unit vector. Because this current is vertically downwards, right now it is along negative y-axis, then unit vector I must write minus j hat cross vector equals to magnitude multiplied by unit vector. Vector B equals to B into I hat. Vector B equals to B into I hat. Correct? And now tell me, it is ILB, but j hat cross I hat is minus k hat. J hat cross I hat is minus k hat, but here one minus sign is already there. So, minus minus plus k hat. And what do you mean by plus k hat? Direction of this force is along positive z axis. Positive z axis means coming out of the plane of the figure perpendicularly. That is why I am putting symbol of dot, which indicates direction of vector F2 perpendicularly outside the plane of the figure. And if you want to find out its direction using right hand palm rule, then also you can find it. Come on, this is right hand, this is palm. I have shown these fingers along magnetic field and thumb along direction of current. Now, in this case, the perpendicular coming out of this right hand palm will be coming out this way, correct? And that will show you direction of vector F2. So, direction of vector F2 is perpendicularly outside. So, I am putting dot, it is along positive z axis. So, unit vector is k hat, correct? Similarly, magnetic force exerted on side SP, let it be vector F2 dash. Come on, vector F2 dash. It is current into length vector, but because this direction of current and this direction of current are opposite, I am just giving symbol here vector L dash cross vector B, correct? Now, this I as it is, what about length vector? It is magnitude of length multiplied by unit vector in the direction of current. This length SP is also L only, and what about direction of current? It is vertically upwards, right now positive axis. So, unit vector you must write j hat cross vector B equals to B into I hat, B into I hat. And now, it is ILB, but j hat cross I hat is minus k hat. J hat cross I hat is minus k hat, correct? Fine. Now, these two vectors have same magnitude, ILB each, same magnitude. But so far direction is concerned, they are opposite. This is along positive z axis, this is along negative z axis. How will you find out direction of this using right hand palm rule? Very simple. Come on. This is right hand palm, fingers are pointing in the direction of magnetic field, in the direction of magnetic field, correct? And thumb is pointing in the direction of current. Now, in this case, whatever is the perpendicular coming out of this right hand palm, the way it will come out this way, no, this way, but you know, whichever direction is coming out of this right hand palm perpendicularly coming out, that direction will go inside the plane of the figure perpendicularly. Inside, that is why I am putting symbol of cross, correct? And that cross indicates inside the plane of the figure perpendicularly, that is along negative z axis. So, unit vector is minus k hat, got it? Now, tell me, these two vectors have equal magnitude, but opposite directions, they are called opposite forces. That is why mathematically you may write vector F2 equals to minus of vector F2 dash. Vector F2 equals to minus of vector F2 dash, correct? Now, try to understand this small figure very accurately, because it is very important now. Midpoint of this side I am taking as point C. Midpoint of this side I am taking as point D, okay? And this line segment CD, which is parallel to PQ, I have shown here. In the now same line segment, I just shift, I bring it here, correct? This is point C, this is point D, and this CD, or measurement wise it is equal to PQ. Measurement wise it is equal to PQ, but PQ equals to B, correct? So, this distance is also small b, this is small b, correct? Now, tell me, how would you see this triangle? Not in the plane of the figure. No, you are supposed to consider plane of this triangle perpendicular to plane of the figure. Perpendicular to plane of the figure. How? I am showing you. Look. Actually, this triangle is like this. Okay? What you notice in the figure is like this. But you should not consider it like this. You should consider it like this. Correct? That is perpendicular. Perpendicular to plane of the figure. Perpendicular to plane of the figure. Correct? I am showing you. Look here now carefully. Come on. Identify the vertices now. Identify. This point is point C. Correct? That point C is here. Got it? This point is point D. That point D is this. Point D is this. Okay? And where is the right angle? Right angle is at point E. Right angle is here. Right angle is here. So this must be point E. Correct? Now tell me. At point C, what is the direction of vector F2 dash? Going inside. Going inside. This way. So at point C, direction of vector F2 dash is going inside. Inside the plane of the figure perpendicularly. Correct? At point D, where is direction of vector F2? Perpendicularly out of the plane of the figure. Perpendicularly outside. So symbol of dot. So at point D, the direction of vector F2 is perpendicularly outside. Perpendicularly outside this way. Correct? Now tell me. It is in this direction. Perpendicularly outside. Got it? Fine. This is the direction of vector F2. This is the direction of vector F2 dash. Now you can see line of action of this force is this. Correct? And line of action of this force is this. Correct? So now these two are the parallel lines of action. This is for F2 dash and this is for F2. So vector F2 dash is acting this way, vector F2 is acting this way. Got it? And now between these two parallel lines of action, you can see this much is the perpendicular distance. Come on, between these two parallel lines, this much is the perpendicular distance. This is point C, this is point E. So what is this perpendicular distance? CE. Line segment CE will give you perpendicular distance between these two parallel lines of action. Correct? So from C to E, this line segment CE will give you perpendicular distance. Look here, perpendicular distance. Correct? Now let me find out that perpendicular distance. I am showing you. For this plane of the coil, the corresponding area vector is like this. You know, area vector is always to be shown perpendicular to the plane of the coil. A plane of the coil is like this. Correct? Perpendicular to this plane, you can think of area vector like this. Correct? Fine. The same area vector I have shown here. And this is now magnetic field. An angle between area vector and magnetic field we show by symbol theta. Correct? This is perpendicular to this. So angle between these two is pi by 2, in which this much angle is theta. So remaining must be pi by 2 minus theta. Pi by 2 minus theta. Correct? And now compare this figure with this figure. This direction is horizontal. This direction is also horizontal. Correct? Parallel to this is this. Parallel to this is this. Parallel to this is this. So whatever is the angle between these two, here, same angle must be here between these two. What is this angle? Pi by 2 minus theta. Then this angle also must be pi by 2 minus theta. Correct? This angle is pi by 2. This angle is pi by 2 minus theta. So this must be theta. Because addition of these three has to be 180 degree. Correct? If one angle is 90 degree, addition of remaining two must be 90 degree, that is pi by 2. If this is pi by 2 minus theta, this must be theta. Correct? Now tell me, you want this perpendicular distance, that is CE. CE. Now opposite to right angle is hypotenuse, which is small b. This angle is theta. Then how would you find out this component? Component of b opposite to theta. Component of b opposite to theta is b sin theta. B sin theta. So perpendicular distance between the lines of actions of vector f2 and vector f2 dash, which was CE, has come out to be b sin theta. Correct? Now tell me, if you have got two forces equal in magnitude, opposite in direction, and which are not collinear, they will definitely produce some torque. And what is the formula of that torque? I am showing you. Magnitude of the torque is defined this way. Magnitude of either of two opposite forces which are not collinear multiplied by perpendicular distance between their lines of action. How will you find out magnitude of the torque? Come on, by a product of magnitude of either of two opposite forces which are not collinear and perpendicular distance between their lines of action. Correct? Come on. This torque we show it by this symbol, tau. The pronunciation is tau, spelling is T-A-U. It is Greek alphabet. Okay, tau. What about magnitude of either of two opposite forces which are not collinear? You may find out magnitude of this or this. They both are same. Here also ILB, here also ILB. I am supposed to write magnitude of either force. So I am writing ILB multiplied by perpendicular distance between the lines of action. And that perpendicular distance we have found out, it is b sin theta. B sin theta. Correct? And such a product is called torque exerted on the coil. Correct? Now let me rearrange it properly. I into L into small b into capital B into sin theta. Correct? I hope you must have understood why I did like that, because L into small b, small l into small b can be replaced by capital A, which is area of 1 ton. So I just replace this LB by capital A into B into sin theta. Correct? This much is the torque exerted on that coil, provided it has only 1 ton. But in the same coil, if there are capital N number of identical tons, each made up of very thin wire and very adjacently located, then through 1 ton if you are passing current and if you are getting this much torque, then through n number of tons you will be getting torque n times than this torque, n times than this torque. So you must multiply this torque by capital N, which is total number of tons. So I have written this B, then I, then A, then sin theta. I have simply multiplied by capital N. This is in general. Okay? If number of tons is 1, you may write capital N equal to 1. Okay? Fine. Now this tau is nothing but magnitude of vector tau. This N into I have written as it is, but A B sin theta, you have studied in first semester. A into B into sin theta indicates magnitude of vector product vector A cross vector B. So magnitude of vector product vector A cross vector B. Correct? Now just remove sign of modulus from both the sides. When you remove sign of modulus, left is here vector tau, here Ni as it is. When you remove this sign of modulus, it will give you vector A cross vector B. Correct? Now this part is pertaining to a given coil, because this is total number of turns in a given coil. This is current passing through given coil. This capital A is area of 1 ton of given coil. So this whole part is pertaining for a given coil. Then we just replace it by another symbol, vector mu, where vector mu is given a specific name. It is called magnetic dipole moment of given current carrying coil. Magnetic dipole moment of given current carrying coil. Correct? So this is called magnetic dipole moment, shown by symbol vector mu cross vector B. So this is the final formula of vector tau which we are looking for. Vector tau equals to vector mu cross vector B. But now if somebody is asking you what is the direction of this torque, it is in the direction of vector A cross vector B. Now let us find out the direction. Vector A is right now this way, vector B is this way. Actually speaking, situation is like this. This is vector B, magnetic field in this direction, correct? What about vector A? Vector A is like this, vector A. Now think of a plane passing through vector A and vector B, it will be this plane. Think of perpendicular screw, correct? Right-handed screw this way. And now you are supposed to rotate this screw in a manner, first vector rotates towards second vector. In this order, first vector is vector A, second is vector B. Vector A is first vector, vector B is second vector. I am supposed to write first vector towards second vector this way, correct? So the manner of rotation is this, and in the same manner, if you rotate this right-handed screw this way, correct, then it will advance vertically downwards. Because it advances vertically downwards, direction of vector A cross vector B or direction of vector tau is right now vertically downwards in this direction, correct, is vector tau. Now tell me, somebody of you may think this way, why we are taking vector A in this direction? Can't we take it on this side? No, there is a rule for that, I am showing you. If coil is like this, then at present I have taken vector A this way, correct? But if you take direction of vector A this way, you will get direction of vector tau in the same condition like this. No, it is not true, because there is a rule for finding the direction of area vector. What is the rule? I am showing you. What is the axis of this coil? Axis, geometrical axis of the coil means an axis passing through center of the coil and perpendicular to its plane. Now hold this axis of coil in the right hand palm such that finger should take the turn in the direction of current. Then whatever is the direction shown by the thumb becomes the direction of area vector. So right now current is passing this way, correct, this way, correct. So I must hold this axis in my right hand palm such that finger should take turn in the direction of current. Then the direction shown by the thumb is this direction, this way. That's why vector A I have shown in the same direction, correct. Now tell me, if you revert the direction of current, suppose you pass the current in this direction, correct, then the same axis you must hold with the right hand palm this way, correct. Finger should take the direction of current, finger should take the turn in the direction of current. Then the thumb will show you this direction. So at that time vector A will be like this, and if vector A is like this, correct, this is magnetic field, this is magnetic field, this is vector A, correct. Vector A is like this, vector B is like this. You want vector A cross vector B, vector A cross vector B to find out direction of vector tau. So this is vector A, this is vector B, find out vector A cross vector B. In that case it will be vertically upwards. So direction of vector tau will be vertically upwards, provided you are passing current in the opposite direction, got it. So in which direction torque will be exerted, that depends on in which direction you are passing the current through the coil, got it. What about SI unit of this magnetic dipole moment? It is SI unit of area and current, that is for area it is meter square, for current is ampere, so it is ampere into meter square, ampere into meter square, got it. Fine. Come on my dears, now we go for question number 20. It is about moving and pivoted coil type galvanometer. Moving and pivoted coil type galvanometer. First of all, let me give you introduction of this galvanometer. It is a very important electrical device with the help of which we can check the presence of electric current in a circuit. How? I am showing you. Suppose some current is passing through this conducting wire, okay. Then that current is not visible, we cannot see that current. So how we are sure whether current is really passing or not? How to check, how to verify? For that, at least don't give me that sort of advice that sir, by touching we cannot find out. Sometimes it may cause your life also, okay, it would be dangerous. So don't do that. In that case what we should do? We should connect some current meter in the way in which the pointer will give you some deflection. If pointer gives some deflection, meaning thereby current is flowing. If pointer does not deflect, then no current is flowing, okay. So basically galvanometer is used in the circuit to check the presence of small value of current passing in the wire, okay, passing in the circuit. Got it? Fine. Now, in the construction of galvanometer, we will see just now some copper coil is used. It has some resistance which is called internal resistance of galvanometer, shown by symbol capital G. It is of the order of 100 ohms. Around 100 ohms, the practical galvanometers have their resistances. Okay. Now, in the textbook, they have shown this figure, which is there in our syllabus to understand, to remember. But then, unless and until you study this figure, you cannot understand this figure. Okay. This figure is very much essential for understanding point of view. I would like to explain you this figure. Okay. I have taken special pain to draw this figure. Now, I would like to explain you the real construction of the galvanometer from this figure, which is called front view. Okay. Not in our syllabus, for examination point of view. From examination point of view, this figure is there in the textbook. It is to be prepared and it is called top view. How to get this top view from this front view, I am showing you. In the construction of this galvanometer, what we do? First of all, we take some non-conducting rectangular light in weight frame, correct? We take one rectangular frame which is non-conducting and very light in weight. Okay, fine. Now, on that frame, what we do? We just wind thin isolated copper wire very closely to have its rectangular turns, and that is why we call it rectangular coil, because its turns are rectangular. Fine. Now, you may show any number of turns in that rectangular coil. Here I have shown only 2 turns. That rectangular coil is here. Okay, fine. These are its turns. That coil is given symbol capital C. Here on the axis of this coil, at the central position, we keep some soft iron cylinder. Okay, fine. Capital R is soft iron cylinder. Now tell me, this coil is pivoted between these 2 pointed supports, correct? Those supports are A1 and A2, and through those supports, the terminals which are taken out for the connection of this galvanometer in the circuit are T1 and T2. T1 and T2. They are the terminals. Okay, fine. Then we just have 2 spiral shaped elastic springs, S1 and S2, tied at the 2 ends of the coil. This is upper spring, this is lower spring. Both are wound in just opposite manner. If this is wound, as you view from the top, if it is found anti-clockwise, then this is wound clockwise, like that. Okay. Then here we just tie up one pointer which can deflect quite freely on this calibrated scale. This is all about the construction of a galvanometer. Which type galvanometer? Moving and pivoted coil type galvanometer. How to get this diagram from this diagram? Now, my dears, this is the top view of this figure, which is there in our syllabus. You must understand now. Architects call it bird's view. Why? If any bird is flying above some tall building, and if that bird happens to look downwards, then whatever view the bird will get in its eyes, that view is known as bird's view. Okay. How will you get this bird's view from this figure? I am showing you. When you view from top in the downward direction, you will find these concave edges of 2 cylindrical concave poles, and those concave edges I have shown here. Correct? Fine. When you view this figure from top, you will find this circular edge on the top of this cylinder, soft iron cylinder. That circular edge is this. Correct? When you view this figure from top, you will find these sides of the rectangular turns, these sides. Correct? And those sides are shown here. Fine. Then when you view this figure from top, you will find this spiral spring, that is upper spring S1, here it is, spring S1, and when you view from top, you will find this pointer, that pointer is here, and the scale also I have shown. Okay. My dears, I have taken immense care to draw this figure, because you can see even I have not changed the color. For the concave poles, I have shown pink color, here also pink, correct. For this soft iron cylinder, I have shown blue color, here also it is blue. For this tons, it is orange color, then here it is also orange. For this spring, it is green color, here also it is green color, correct. Then for this pointer, yellow color, here also pointer is shown with yellow color, scale with white color, inside the calibration you will find with purple color, same color here also, white colored scale, and the calibration is done in terms of, with the color purple color. Okay, fine. Now, let us start the working of this device. Okay. When you connect this galvanometer in the circuit, either current will pass this way or it will pass this way. That is, current will pass from T1 to T2 or from T2 to T1, correct. But that current will certainly pass through the coil, and whenever current is passing through the coil, it will be exerted upon by some torque given by this formula B na sin theta, correct. So that much external torque is exerted on the coil. Because of external torque exerted on the coil, it so happens it just gives some angular deflection. Okay, it starts showing you more and more angular deflection. But then, as this coil gets deflected, then there is a winding, there is a more twist, there is some twist in this elastic springs. Okay, and because of the twist produced in the spiral springs, it so happens there is some restoring counter torque developed in the springs. But that counter torque is such that when you remove external torque, because of the help of that torque, it will restore its original condition. That's why we call that counter torque as restoring torque. Okay. So because of property of elasticity, some restoring torque is developed in these two elastic springs, correct. Amount of restoring torque developed in a given elastic spring per unit angular twist is called its torsional constant, shown by symbol small k. So per unit angular twist, if k amount of restoring torque is developed, then for 5 amount of angular twist, what restoring torque is developed? This into this upon this. So it will be k into 5. So this much is the restoring torque developed in the spring. Now tell me, the external torque is constant. External torque is constant, correct? But then because of the external torque, the coil deflects. As the coil deflects more and more, there is more and more restoring torque developed in the elastic spring. At one stage, the restoring torque becomes equal to external torque. That is the condition of equilibrium. At that stage and then after, there is no further deflection of the coil possible, and in that steady position, whatever is the angular deflection of the coil, we take it phi. Then for 5 amount of angular twist, what is the restoring torque? It is k into 5. Okay. So in that equilibrium condition, which two torques have become equal in magnitude? External torque and restoring torque, correct? External torque is B na sin theta, restoring torque is k phi. Then you must be asking, why theta is taken 90 degree here? I am showing you. Why theta is 90 degree? I am showing you. Look here. Here we have kept these two magnetic poles concave, and we have introduced soft iron cylinder at the center for one specific purpose, and that specific purpose is to obtain radial magnetic field. Now what do you mean by radial magnetic field? I am showing you. this soft iron cylinder has very high value of permeability, correct? And because of very high value of permeability, it has got very strong attraction for magnetic field lines. So as soon as magnetic field lines emerge out of this north pole, they are first attracted towards this soft iron cylinder, and then after they are allowed to approach the magnetic south pole, correct? Fine. Now here, if you consider some circle here, correct, some circle, then for that circle, these are the magnetic field lines which are arranged along the radii, and because these magnetic field lines can be considered to be along the radii of this circle, we call this magnetic field as radial magnetic field, okay? Radial magnetic field. Now what is the benefit achieved by radial magnetic field? I am showing you. See, when you pass current through the galvanometer, that current will pass through the coil, will produce some deflection of the coil. So now, before passing current, you may find the coil in this situation, correct? And this side is shown here. This and this side are inside the plane of the figure, and this side is on the back side. Only this side you can see here, okay, before passing current. But as soon as you pass the current, this coil is getting deflected. So now after deflection, it may deflect this way or it may deflect this way, correct? Suppose it deflects this way. Now this is the steady position of the coil under equilibrium. Now tell me, how do you draw area vector perpendicular to the plane of the coil? It will be like this, correct? And here the external effective magnetic field is this. When the position of the coil is like this, the external effective magnetic field is in this direction, in this direction. So the situation is like this. This is the direction of magnetic field in this direction, and this is the direction of area vector. How to find these two? Mutually perpendicular, correct? If the coil is getting deflected this way, suppose, correct, from this position it is getting deflected this way, then come on, effective magnetic field is this way, correct, this way, and the area vector will be like this, correct? So the situation is like this. This is area vector, this is magnetic field. They are mutually perpendicular, correct? So what I mean to say, whether coil remains like this or gets deflected this way or this way, for any angular position of the coil, vector A and vector B remain definitely mutually perpendicular because of radial magnetic field. But tell me, when you will have radial magnetic field, provided you are keeping soft iron cylinder in the central position and you are keeping these two magnetic poles with concave shape, correct? That was the purpose of introducing the soft iron cylinder and keeping the magnetic poles concave, okay, fine. So now tell me, angle between vector and vector B is theta, which remains here 90 degree in any angular position of the coil. So that's why I am writing theta equal to 90 degree. Now this is external torque, this is restoring torque, both of them have become equal and the coil has settled to the equilibrium condition, okay. So at that time 5 is called steady angular deflection, steady angular deflection. Sin 90 is 1, find out 5 from here, it is B N A upon K into I, B N A upon K into I. Tell me, this bracketed part is constant, and because this bracketed part is constant, if you remove it, then phi is proportional to I, phi is proportional to I. This is very essential condition required for any current meter to measure current, because when you are not passing current through that current meter, I is 0, then deflection also must be 0. If you are passing less amount of current, you must get less deflection. If you are passing more amount of current, you must get more deflection, correct? And that linear relationship we have got here because we could make theta equal to 90 degree. Why theta was made 90 degree? Because of radial magnetic field. And just to have radial magnetic field, we made this magnetic poles concave and we had introduced soft iron cylinder in the way, correct? Got it? Fine. Now, when you get steady angular deflection, if it is less, current passing through the galvanometer must be less. When you get more angular deflection, come on, current passing must be more. So, this is how indirectly by measuring or by observing the angular deflection, we can measure the amount of current passing through the galvanometer, correct. Some specially designed galvanometers can measure small value of DC, got it, fine. Whatever is the resistance of this entire coil, it is called internal resistance of the galvanometer, shown by symbol capital G. It is around 100 ohms, okay, fine. Now we go for what is called sensitivity of galvanometer. What is this 5? Steady angular deflection. For how much current passing through the galvanometer? For current I. You just divide steady angular deflection by current passing through the galvanometer. Then you get angular deflection produced in the galvanometer, means in the coil of the galvanometer, per unit current passing through it. That ratio itself is known as sensitivity of a galvanometer. Deflection observed in the coil of a galvanometer or deflection observed in the pointer of a galvanometer per unit current passing through it is called its sensitivity, shown by symbol S, correct. Find out phi upon I from here. Phi upon I will be B N A upon K, B N A upon K, correct. Find out now SI unit of sensitivity. It is angle upon current, so it must be radian upon ampere, got it. My dears, what was small k in this theory? It was torsional constant. What about its SI unit? Tell me, what was this K5? It was restoring torque. Restoring torque is K into 5. Now, if you want SI unit of K, you should find out SI unit of torque upon angle. What is SI unit of torque? It is Newton into meter. For angle, it is radian, correct? So, remember, for torsional constant, its SI unit is Newton into meter upon radian. Got it? Fine. Come on, my dears. Now, let us go for question number 21. It is about difficulties while using galvanometer directly as a current meter and its solution. Look, last time we had seen about the design of moving pivoted coil type galvanometer, correct? Now, in practice, what do we find? That you cannot use that galvanometer directly as a current meter. Why can't you use it directly as a current meter? What is the reason? We face 3 difficulties while using that galvanometer directly for the measurement of current. Which are those 3 difficulties? Let us see one by one. First, current cannot be measured accurately using galvanometer. Why? What is the reason? Look, suppose I have one resistance R connected with this battery having EMF E, okay. Current starting from positive terminal of this battery is suppose capital I, which is the actual value of current which I want to measure using galvanometer, okay. Then naturally in this circuit I must connect galvanometer in such a manner such that the current to be measured must pass through the galvanometer, then only it can measure it, correct. But for that purpose I must connect galvanometer with this resistance in series, then only the current to be measured will pass through this galvanometer and then it can be measured, correct. But you can see in the diagram, this type of connection of G with R is nothing but series connection, okay. So, remember, whenever you use any instrument, any device as a current meter, that current meter is always to be connected in series. Current meters are always connected in series, okay, fine. Now, what is the problem here? I am showing you. Initially, before you have connected the galvanometer, the resistance offered to this battery was simply R, correct? But afterwards, after connecting galvanometer, final resistance offered to the battery is series connection of G and R. And in case of series connection, what is the equivalent resistance? It is the summation of individual resistances. So it is now R plus G, correct? Earlier it was only R, now it has been increased to R plus G, where G is the resistance of galvanometer which is connected in series. Okay, fine. Now tell me, earlier it was R, now it is R plus G, so resistance has been increased. Naturally, when resistance will increase, current will decrease. So this current is smaller than this current. I am saying that I dash will be less than I, correct? I dash is less than I. Now tell me, when I dash is less than I, it means to say I dash is not equal to I. What is I dash? It is that current which is measured by this galvanometer. What is I? It is actual current. But measured current is proved to be not equal to actual current. When measured current is not equal to actual current, what does it mean? Current cannot be measured accurately, correct? Then what to do? If you want to measure current 100% accurately, then in ideal condition, you can make resistance of current meter to be 0. If ideally you think of value of G becoming 0, then you just put that value here, correct? Then R plus 0 will be R only. So earlier also it was R, now also it is R. Even after connection of current meter, if the resistance remains same, then current passing through the battery will also remain same. In that case, I dash will be equal to I, then measured current will be equal to actual current. Current can be measured 100% accurately, provided you can make resistance of current meter to be 0. But that is not possible in practice. That's why I have written here under ideal conditions. Okay, fine. So if any current meter wants to measure current accurately, 100% accurately, then its resistance should be 0, which is not possible in practice. It is under ideal condition. Okay, but then in practice what we should do? In practice what you can do, you can minimize the resistance of current meter. That is, mathematically you can make G tending to 0, correct? When G tends to 0, then R plus G will tend to R, and if R plus G tends to R, then final and initial resistances will be nearly equal. Then I dash will be nearly equal to I. When I dash is nearly equal to I, then measured current is nearly equal to actual current. Current can be measured almost accurately, correct? So now onwards, remember, for any current meter, its resistance should be made as small as possible, then only it can measure current accurately, correct? Fine. What is the second difficulty while using galvanometer directly as a current meter? Second difficulty is this: in practice, the current capacity of galvanometer is found to be very small as 1 microampere, that is 10 raised to minus 6 ampere, correct? What do you mean by current capacity? The maximum value of current which can be passed safely through a given instrument is called its current capacity. When you pass 1 microampere current, that is 10 raised to minus 6 ampere current through a galvanometer, it gives full scale deflection, meaning thereby you should not try to pass current more than that limit through that galvanometer, correct? It is its current capacity. Then what does it mean? That we cannot pass large value of current through the galvanometer. That is its difficulty, that is its limitation, okay? That is our difficulty and its limitation, fine. Third problem we come across, you know the formula of Joule's heat. In the previous chapter we had obtained capital H equals to I square RT. Remembered? When I value of current passes through R resistance for T time, what is the amount of Joule's heat developed in that? I square RT. Now tell me, if you pass large value of current through the galvanometer, then this amount of Joule's heat will be very large, and in that case there are chances for the coil of that galvanometer to get burnt, okay? So there are chances for breaking of the coil or for burning of the coil when you try to pass current through a galvanometer with large value which is more than its current capacity, okay? So totally 3 difficulties we face while using galvanometer directly as a current meter. Okay. Then tell me what to do now. We should try to remove all these difficulties, and then we should try to reconstruct a new better current meter, but it should be such that it can measure large value of current safely and that too very accurately. Okay. Such a current meter we have designed in practice. It is none but an emitter. Now let us see how to convert given galvanometer into emitter. So let us go for design of better current meter called emitter. Look, conversion of galvanometer into an emitter. Conversion of galvanometer into an emitter. I am showing you how to convert. First of all, you do one thing. With this given galvanometer, you just connect one resistance in parallel with value very much smaller than resistance of galvanometer. That very small resistance connected in parallel is called shunt, shown by symbol capital S. Value of S is very much smaller than capital G. Okay. How would you define shunt? An extremely small value of resistance connected in parallel with given galvanometer is called shunt. Or you may define it this way also. A resistance connected in parallel with given galvanometer with value of resistance very much smaller than resistance of galvanometer is called shunt. A resistance connected in parallel with galvanometer with resistance very much smaller than resistance of galvanometer is called shunt, shown by symbol S. S value is very much smaller than G. Correct? Now you can ask me, by connecting this very small resistance in parallel, how these problems are removed, how these problems are solved. I am showing you. First of all, tell me, don't you know one fact, that in a parallel combination of two resistances, the equivalent resistance will be smaller than smallest, smaller than smallest. For example, here, this resistance I just assume, look here, say 100 ohm, okay, and suppose this resistance is 0.01 ohm, okay. This is 0.01, this is 100. This resistance is 10,000th part of this. This upon 10,000 will give you 0.01, correct? I mean to say this resistance is very, very small. Now for a parallel combination of two resistances, equivalent resistance will be smaller than smallest, smaller than smallest. Among these two, this is the smallest, and now equivalent resistance will be still smaller than this. Suppose it is 0.0099, correct? 0.0099, which is very small as compared to this. Okay, I mean to say, if you don't connect this, then this resistance is 100 ohm. If you connect this, then this parallel combination will have resistance 0.0099, which is very small, nearly zero, And just now you had concluded, for accurate measurement of current, the resistance of current meter should be made as small as possible. That is what we have done. So now this parallel combination can measure current very, very accurately. So your first problem is solved, correct? What was second and third problem? When we tried to pass large value of current through the galvanometer, it was getting damaged. Now that damage will not be there. Galvanometer will be saved from the possible damage. How? I am showing you. Through this parallel combination, I just pass total current, say capital I, which is very large as compared to current capacity of this galvanometer, shown by symbol Ig. Value of I just take very much greater than Ig. What is Ig? It is old current capacity. Old current capacity means before connecting shunt. And what is I? New current capacity, that is after connecting shunt. Okay. Now this is a very large value of current. Now though you are passing large value of current, then also this galvanometer will not be getting damaged, because when this large value of current will come up to this junction, after that it is offered two branches. One is this, another is this, correct? But you know, in whichever branch resistance is very small, through that branch current would like to flow majority. So what happens out of this total current? Majority of the current is diverted through shunt. It flows through shunt, and because majority of the current is bypassed this way, now the current passing through galvanometer is very small, and because very small current is passing through the galvanometer, it will not be getting damaged. Okay. So this is how, by connecting a proper shunt, we are saving this galvanometer from the possible damage. Correct? Fine. Now there won't be any breakage of the coil, there won't be any burning of the coil in this galvanometer. In short, it will be saved from the possible damage. Okay. But now, how to find the exact value of this shunt? For that, you will require to derive its formula. So now let's go for derivation of formula of shunt. Very simple. Here we have connected that value of shunt such that when we pass current I through this parallel combination, the current passing through this galvanometer is just equal to its current capacity, and remaining current, that is I minus Ig, will pass through the shunt, and it is shown by symbol Is. Okay. Now apply Kirchhoff's first law at this junction A. Kirchhoff's first law is sigma I equal to 0. Current flowing towards the junction is to be taken positive, currents flowing away from junction are to be taken negative. So I is taken positive and Ig and Is are taken negative. I is positive, Ig and Is are taken negative, and that algebraic summation will be 0. Correct? Now transfer this minus Is on this side will become plus Is. So Is equals to I minus Ig, give it equation number 1. And now in this closed path A, B, C, D, A to B to C to D to A, you just apply Kirchhoff's second law, sigma IR equals to sigma E. Come on, sigma IR equals to sigma E. Go this way. Correct? In the direction of current, so IR product should be taken negative, minus Is into S. Minus Is into S. Correct? And now when you go this way, come on, you are going opposite to current, so IR product should be taken positive, plus Ig into G, plus Ig into G. Correct? And then in whichever closed path you have taken algebraic summation of IR terms, in the same closed path we should take algebraic summation of EMFs. But in this closed path there is no battery, no EMF, then sigma E should be taken 0. Correct? Transfer this, will become plus Ig into G will be equal to Is into S. Correct? Give it equation number 2. Even if you don't apply Kirchhoff's second law, straight way also you can write down this equation, because don't you know, voltages across the components connected in parallel are always equal. These two are connected in parallel, so voltages across them must be equal. Whatever is the value of Ig into G, same will be value of Is into S. Ig into G equals to Is into S, give it equation number 2. Now we require formula of shunt. Okay, find it, come on, derive its equation. It is Ig into G upon Is. Ig into G upon Is. Correct? Ig into G as it is. What is Is? Is is, look, Is is I minus Ig. Is is I minus Ig. Correct? This is the required formula of shunt. For what purpose you are connecting shunt? Just to increase the current capacity. What was current capacity of this galvanometer? It was simply Ig, which was very small. We want to increase it to I, where I is very much greater than Ig. For that you require to connect extremely small value of resistance in parallel, but what is exact value, that you can determine using this formula. Okay, fine. For example, the current capacity of given galvanometer is suppose 1 milliampere, that is 0.001 ampere. Okay. The new current capacity we require suppose 10 ampere. Resistance of given galvanometer is suppose 100 ohm. Put these three values here. What is I value? 10 ampere. What is Ig? It is 0.001 ampere. What is capital G? 100 ohm. Put them here. Find out S. Exactly you will get it. The value of S comes out to be nearly equal to 0.01 ohm. 0.01 ohm. Okay, fine. Now tell me, this is the value of shunt, 0.01 ohm. Suppose you are finding this shunt, means it will give you emitter? No. This much value of resistance you must connect in parallel with given galvanometer. Correct? Suppose you have connected, means it will give you emitter? No. Still the main job is left out. What is that main job? To calibrate the scale of galvanometer in terms of ampere, because you require ammeter, correct? Now how that calibration is done, it is not explained in textbook. I would like to explain you very much in detail. Pay your very nice attention on the screen, please. Now we are going for calibration, okay? Here I am writing total value of current, correct, which is passed through the parallel combination. Here I am writing current passing through galvanometer, fine. And here I am writing deflection in divisions, deflection in division, okay, fine. Now suppose 1 ampere current is passed through this parallel combination. What we do now, we pass known currents through this parallel combination. Let it be first of all 1 ampere. When you pass 1 ampere current here, the current passing through galvanometer will be 10,000th part of this, because this resistance is 10,000 times than this resistance. Look here, compared to this value, this resistance is 10,000 times. Because this resistance is 10,000 times than this, then current passing through this will be 10,000th part of this current. 10,000 part of this current is 10 raised to minus 4 ampere, correct? And that much current, when it passes through galvanometer, will produce some deflection. Suppose the deflection notice is 10 divisions, okay? Now you increase this known current, let it be 2 ampere. When you increase this current will also increase. And when current passing through galvanometer increases, it will increase the deflection. Suppose it is now 20 divisions. When you pass 3 ampere here, suppose here deflection in division is suppose 30 divisions. Like that you can increase it up to 10 ampere, correct? At that time, here you are going to get maximum deflection, that is 100 division. And at that time, current passing through galvanometer is 10 into 10 raised to minus 4 ampere, that is 10 raised to minus 3 ampere, that is 0.001 ampere, which is its current capacity, okay? Now if you pass this current more than 10 ampere, then current passing through galvanometer will be more than its current capacity, then it will be getting damage, okay? We should not do that. Now when you pass 1 ampere current here, the deflection observed here, it is 10 divisions. So wherever it is 10 divisions, there you must write 1 ampere on the scale, because this current is 1 ampere. So I am writing here 1 in ampere. Similarly, when you pass 2 ampere, deflection observed is 20 divisions. From 0 up to this limit, there are 20 divisions. There, because this current is 2 ampere, I must write 2 ampere on the scale, 2 in ampere, correct? This is how I calibrate the scale of galvanometer in terms of ampere. Now it is ready for the use. What you can do now, you can pass unknown current here, unknown current, suppose x ampere, and by passing unknown current, what you are supposed to do, you are supposed to simply observe the deflection in the galvanometer, okay? Suppose you observe 20 division deflection. How much? 20 division, correct? Now go reverse. When deflection in division is 20, then what must be current passing through galvanometer? It must be 2 into 10 raised to minus 4 ampere. So Ig must be 2 into 10 raised to minus 4 ampere. But when 2 into 10 raised to minus 4 ampere current will pass through galvanometer, provided total current is 2 ampere. So that time total current must be 2 ampere. So your unknown current has come out to be 2 ampere, correct? So at that time, when you pass unknown current, the pointer would deflect up to this limit, which indicates total current to be 2 ampere, correct? So this is how current is measured in ampere. That's why this parallel combination can be taken as ammeter. Right from beginning, if you would have calibrated the scale of galvanometer in terms of microamperes, then you could have got microammeter. If you could have done the calibration in terms of milliamperes, you could have got milliammeter, correct? This is how, by calibrating the scale of given galvanometer properly in ampere, milliampere and microampere respectively, we can get ammeter, milliammeter and microammeter. Look here, ammeter, milliammeter and microammeter. Got it?